Good morning, everyone. Thank you for attending this final event of Cobra project. My name is Rochdi Mazuki. I'm professor at University of Lille, and I am the scientific coordinator of Cobra project. We are happy to welcome you today to present you all our research results through this Cobra project. In the same environment where we launched it 5 years ago. So it's challenging for us to present you or to share with you a lot of information in short time and in hybrid modes. We hope that at the end of this event you will appreciate the organization of this event and all the results. So during the coming 1 hour and a half, we all the partnership of Cobra project will present their main outputs and results. Then we follow with the online demonstration of the Cobra robot with our actual team, and then we can go after that to a round table with the next international panels which represent scientists, clinicians, and industrials for 1 hour, and then we finish by 4 p.m. After that we can go after a break, we can go to visit the common platform of Cobra brachytherapy. So shortly, I want to introduce you the framework of Cobra project and the context, and then I let the partners exposing their main results. Okay, Maximilian. Okay, now this is for 3 p.m. the round table with all the participants. We will have 4 participants physically here present and 5 excellent. Good. So Cobra project is a project supported by an European program called Interreg 2C. This program support collaborative project from 4 regions of Europe: the south of UK, the north of France, the northwest of Belgium, and the west of the Netherlands. Cobra candidated to the 4th call of the Interreg 2C in terms of programmation 2014-2020, which concern the specific objective 1.2 in terms of increasing the delivery and of innovation for smart specialization. In our case, it concerns the life science and health. So the main challenges of Cobra project concern are in relation to the cancer control plan. This concerns cross-border countries, or almost cross-border countries here in the region of the 2Cs. The Cobra project focused mainly on the prostate cancer, where it affects 1 on 6 men between 60 and 79 old, and this cancer represents the 3rd death from cancer in human in the region of the 2C. The Cobra project challenge concerns the development of technological innovation, which help the development of new devices for diagnosis and treatment of localized cancers, allowing increasing the quality of the life of patients and reducing the cause and mortality. So the technically means we wanted through this project to develop a technology of mini-invasive robot, allowing which is controlled through MRI, allowing to perform the brachytherapy and the biopsy inside this complex environment of MRI. So Cobra outputs concerns four items. One, technically, it's about the prototype. Through Cobra, we wanted to develop a prototype of sterable technological readiness level of 6. This means that at the end we want to demonstrate we demonstrated with on live animals in terms of initial performances. And the second output concerns the training, that means developing on facilities, even from software or hardware, for the target group, which are medical hospital and medical centers in the region of the 2 Cs. The third output concerns the study of mapping the dispersion of the concerned target, which are the population with prostate cancers in the region of the 2 Cs. This allow, when the result or the solution of Cobra enter to the market, can be helpful to know exactly how we can reduce the disparities between the city and rural regions in terms of accessibility to high quality of treatment and diagnosis for such cancer. And finally, the fourth output concerns the development of network between SMEs, hospitals, and academia in terms of development of technologies related to the or innovation related to the medical technologies. Maximilian, please. Now it works. Okay, so the partnership of Cobra is composed with full partners. What it means full partners, that partners who received co-funding from the program, who are 9 from different classes. You have academic partners, medical partners, clusters, and industrials from 3 countries of the region of the 2 Cs, and 12 observers. These observers provide us expertise in their topics and facilities, specifically from industrials, that we strongly thank them about their contribution in this project. Basically, in terms of positioning, our project idea is coming from how we can improve, how we can associate and collaborate the high quality imaging like the MRI with devices for treatment, like what we see here on this slide. We can see external radiation therapy coupled with MRI. This is the new generation of systems which are ready now in the market, called Amar Linac. We have versus Electa and versus Jure. This is what we apply nowadays as a solution for treatment of cancers under control of MRI. In our case, we by this inspiration, we wanted through the Cobra project to work on the internal radiation therapy in part in terms of treatment. This is what we call the brachytherapy. And our development consists of how we can assist the operator at the end to accurate the deposit of seeds in localized biological tissues in order to reduce the side effects, impotence, for example, and traumata during the insertion, like what we see here manually in this figure. Also to reduce, to improve the reliability and the accuracy of the deposit, and to reduce the displeasure after multiple insertions, like what it exists in the practice or conventionally, and also to minimize the number of insertion through the perennial side, even for the LDR or the HDR brachytherapy. Why why minimally invasive intervention? Yeah, this this is the use of minimal invasive robot for intervention. Yeah, can help clinically in terms of what we see here on the screen: a small incision, yeah, less pain, yeah, low risk of infection, etc., until reducing the blood loss. This is really helpful, or the advantage of localized or mini-invasive solutions. Why now using MRI guidance technologies coupled with this robotized mini-invasive intervention? For mainly 3 reasons. This is what we considered during the Cobra project. It concerns mainly the detection of micro lesions. Yeah, we were only the MRI which can help in detecting such micro lesion comparing to ultrasound solutions. Highly quality of imaging in order to detect or to have a high resolution for on biological tissues. And the last point concerning the exploitation of MRI data toward adaptive tracking of motion for a soft target. Yeah, here you can see two prototype of PRL6. One that we contributed on it in 2014, but it's an ultrasound-based control, and the second one, which is Cobra 1. Yeah, the Cobra project is organized or divided in 4 work packages. You have 2 technically, which is work package 1 and 2, integrated design and diagnosis and treatment, and 3 other peripheral work packages in terms of intellectual properties and technology transfer, entrepreneurship and communication, and finally the overall management. Finally, the budget, the total or eligible budget of the project is around 3.8 million, and we received from Europe 2.3 million to achieve our objectives. Thank you for this long presentation. Yeah, I think that I am more than 5 minutes. Okay. Okay, I let the talk to the next talk. Yeah, will be done with by Sarah from Portsmouth Hospital University in UK. Thank you, Sam.
Okay, so good afternoon. Thank you, Roshdi, for the introduction to the project. The purpose of the next presentation is to give you a bit of an introduction to the clinical background and the relevancy of the Cobra project to clinical practice. So the Cobra project is focusing in the first instance on prostate cancer, looking at both diagnostic biopsies and also therapeutic brachytherapy. And for both of those procedures, we have the opportunity to replace what is currently the manual needle insertion procedure with a robotic technique. And the project is relevant for prostate cancer because this is a body site at the moment that we do an awful lot of biopsies on manually, and also the brachytherapy technique is very well established within the clinics. And statistically speaking, prostate cancer globally, we still have about 1.4 million new cases per year. It's the second most frequent cancer in males, approximately 375,000 deaths per year, and the fifth leading cause of cancer mortality. So it's very relevant for the clinical need. So let's talk a little bit about the current prostate biopsy practice. This is quite a rapidly changing field, and I would say that there's a lot of different techniques at the moment between the different hospitals. So during the biopsy, we are trying to extract a very small amount of tissue, about 2 centimeters long and a fraction of millimeters in diameter. And you can see that on the blue sponges on the right-hand side there, some core examples of the core tissues that have been extracted from the prostate. And this can be done transrectally, so inserting the needles through the rectum wall with the ultrasound probe in the rectum there. But more often than not now, we use a transperineal technique, which you can see in the middle image there. So these can be template guided, as you can see, or they can be freehand. Some urologists prefer to do this freehand without a template to restrict. And depending on the process, there may be a need for a general anaesthetic, in which case the procedure is in the theatres, or it may be a local anaesthetic, in which case it can be done in a clinic room as an outpatient procedure. So the two graphs at the bottom are from the National Prostate Cancer Audit from December 2019. And the graph here just shows the rapid rise in the number of transperineal biopsies compared to transrectal. And the primary purpose for that is to reduce the amount of sepsis that we see with the transrectal approach. And you can see from the bar graph here in blue, so you've got the transrectal on the left and transperineal on the right. And the blue bar represents sepsis, so we can see that that has reduced, which is great. The red bar represents the amount of urinary retention, and there's actually been quite an increase in urinary retention between the two techniques. And one possibility or one reason for that is the number of insertions and the number of cores that are being extracted from the transperineal approach. So ultimately, we want to reduce this, and we want to be able to target and just take fewer samples of the prostate. But in order to do that, we need to be really confident about where we're taking the samples from. So we need to be really confident about our imaging. So generally in our hospital, we've moved from ultrasound to an ultrasound MRI fusion approach. So on the ultrasound images, it's fine for seeing the outside of the prostate, but we don't see any detail internally. We don't see the lesions. We can see the lesions very clearly if we use multi-parametric MRI imaging, and it has a very high specificity. And this image at the bottom just shows the process of having the MRI scan contouring the prostate itself and the lesion, fusion this with the ultrasound, and then in theatre acquiring with the live ultrasound the samples. So how about the brachytherapy practice? Well, it's similar, very similar setup, transperineal approach, and we can use either permanent low dose rate seeds for the implant, or we can use a high dose rate temporary implants, depending on the stage of the disease. Whichever one is being done, we are having to avoid the organs at risk, and you can see in the image here that we're treating the whole prostate with the blue colour wash to 100% of the prescription dose, and we've got higher doses on the left and right, but we're avoiding the urethra in the middle with the high dose regions. So there's a need for precision. So let's think about what the need is with biopsy first of all. The lesions can be very small, as low as 0.5 cc volume, hidden within a prostate volume that can be up to 120 cc. So trying to target that is quite tricky. So the option could be to use template biopsy, but that involves many more insertions with increased potential for urinary retention, and also significantly increased workload for histopathology. So better would be to target it with the MRI imaging, and as proposed by the Cobra project, using real-time MRI only would remove any potential errors from MRI and ultrasound fusion. And how about for brachytherapy? So we have very steep dose gradients around the source, and we are anatomically very close to organs at risk, such as the urethra, the bladder, the rectum, and the neurovascular bundles. So we need to be very precise about where we're positioning the seeds. Furthermore, if the seeds are positioned outside of the prostate, then there's a risk that they can migrate. And also focal brachytherapy is of interest. So this means escalating the dose to the lesions, to the dominant intraprostatic lesions. And in order to do that, we again need to be more precise. We need to be able to see on the imaging where the lesion is to escalate the dose. And there can be some complex lesions to treat. If they're particularly near to the urethra, then they could be underdosed, because that's an area that we try to keep cooler. And also if they're close to the apex, then again, the dose to those lesions can be tricky to cover. So there are some limitations to our current practice. Firstly, as we've seen, there's insufficient information on the ultrasound alone. There's a risk of misaligning the ultrasound and the MRI. There's an error introduced in that fusion process. Difficulties tracking deformations of the prostate glands during the procedure. Straight needles and the template limits the access to various parts of the prostate gland, and there can be obstructions caused by the pubic arch, caused by the angle of the urethra, caused by calcifications. And indeed, we do see interoperator variability in both biopsy and in brachytherapy. So what Cobra is proposing is a number of solutions for these issues. The linchpin of which is the robotic arm, which is fully MRI compatible. And then there are a number of modules linked to this to help solve those issues that have been identified. So we have the automatic seed loader, a biopsy module with the biopsy gun that's MRI compatible, sterable needles to avoid the obstruction issues that we've seen, needle path and seed trajectory mapping software. There's the ability to calculate dose directly onto MRI without the need for the CT information, and the development of bio-inspired phantoms. So during the rest of the workshop, there's going to be a number of presentations to cover each of the following items, and I hope that you enjoy. Thank you.
tour of Martijn Jeffers from TU Delft. He will present his main contribution on sterable nib for LDR brachytherapy. Welcome, Martijn.
So thank you, Horsti. My name is Martijn de Vries from the Delft University of Technology in the Netherlands. And today I will present you our part of the project, which is on sterable needle sterable needle mechanism for low dose rate prostate brachytherapy. So it concerns the brachytherapy module, which is mounted on the robot that is developed by Lille. So if we look at the aim for the sterable needles, we want to increase the controllability of the needle during the implantation. So to counteract perturbations due to needle deflection or tissue deformation, tissue movement, and so on. And we want to increase the reach within prostates with pubic arch interference. And pubic arch interference is actually quite common in larger prostates. So the pubic arch is bone that's laying in between the perineum and the prostate, obstructing mostly the ventral part of the prostate, as we can see over there. And in this way, with sterable needles, we want to deliver a high dose to the target volume, so to the prostate, while sparing healthy surrounding tissues, such as the urethra, the rectum, and the bladder, in patients which are normally excluded from this therapy. But unfortunately, we couldn't find the size of numbers about pubic arch interference, about the depth. We had to overcome during the needle implantation. So we performed our own study together with Portsmouth University Hospital to quantify the pubic arch interference. And we used this to really set the requirements for the needle steering. And we looked into data sets of 27 patients. So we segmented the pubic arch, the prostate, and the rectum. And this was done on the basis of MRI scans with the patient in supine position. And then we found that in 14 of those 27 patients, we had more than 10 millimeters of interference. So the pubic arch was obstructing more than 10 millimeters of the prostate, and those parts were not reachable with conventional rigid needles. And based on the data, we looked at what happens if we go from supine position, which is used for imaging, to lithotomy position, which is used for the procedure. So normally, when you have a brachytherapy procedure, the patient is in a lithotomy position. And this normally increases the accessibility of the prostate. And that was what we found as well, based on the data. But we found that pubic arch interference was still occurring in the lithotomy position, but the amount of pubic arch interference was very patient specific. So it really set a range for us for the amount of steering we wanted to have. So we wanted to have up to 50 millimeters of steering over an insertion depth of 100 millimeters. It's not working. Yeah. So if we look at the design, we actually just used a rod, and we split the rod into 4 segments, 4 quarters, by using wire EDM. And the segments are still joined at the tip, as we can see in the image. And we have an flexible outer needle and a steerable inner needle. And by pushing and pulling those segments, we can manipulate the tip of the needle. And during insertion, the needle shaft will follow the orientation of the tip, and in this way we can have curved trajectories, so we can really steer around the pubic arch and reach those obstructed areas. And we can steer in in multiple planes. So we had 2 rotational degrees of freedom at the tip, and the instrument is suitable for both stranded and loose seeds. So in the top left, we see the initial design, and we made some iterations, and we came to our final design, which you can see in the image. And it contains 4 piezoelectric motors at the proximal end to actuate those segments and allow for needle tip steering. And we used a 2-way port, and one port is used for steering of the needle. And after the needle is placed, we retract the inner needle all the way to the end, and we use the other port for the seed loading of the prostate, because we need to irradiate the tumor, of course. So in this way, we don't have to retract the needle, and we can reach or we can target multiple areas in the prostate without a total retraction of the instrument. So in this way, we can actually include 27 of the patients which are normally excluded from prostate brachytherapy because they have too much pubic arch interference. And we don't need hormonal therapy for these patients, which is normally used to downsize the prostate and make the prostate more accessible. But yeah, due to the steering, we don't need that, and this saves the patient from the bothersome side effects. So we tested the needle, the brachytherapy module in the facility of Philips in Best, and we looked at the distortions on the MRI image, which you can see in the top middle image. And we saw that the shaft only had a distortion in the 3 Tesla MRI of 33%, while the distal tip had a larger artifact, but it's actually quite common to have a blooming ball void at the tip. So yeah, we have to look into how to decrease this distortion, but I think we can conclude that this module is actually MR conditional within the 3 Tesla environment. So in the 1.5 Tesla environment, we probably will decrease the distortion. We did some tests, so in vitro evaluation of the needle system. So we developed a prostate phantom in Delft as well, mimicking the anatomy of a patient with pubic arch interference and mimicking the mechanical properties of tissues. And hopefully the video will start, but I'm not sure. Yeah. So we inserted the needle through skin into the prostate phantom, and then we actuate the segments to orient the tip. We advanced the sterable needle into the prostate, and then we see that we can really steer upwards to reach those occluded areas. And after placement, we retract the inner needle, the sterable inner needle. So we use one port for that, and we can use the other port for the seed loading. So if we look at the integration, this sterable needle system is suitable for MR imaging and can be controlled and inserted by the developed robotic system in Lille. And the output is suitable for experimental evaluation and for dissemination as well. So that's it. Thank you.
Questions?
Yeah.
Hello. Okay. First, thanks for your presentation. And I was wondering about the study you did on the pubic arch interference.
Yeah,
That's it. Is there a difference between the transperineal intervention and the transrectal intervention in this sense? Would you observe less occlusion, let's say, in the transrectal?
Yeah, definitely. Actually, there is no occlusion with the transrectal approach, But if we look at the clinical data, we see that transrectal approaches have worse outcomes for the patient. So that's why Sarah already told about the heading to the transperineal approach, especially for the biopsy, but I'm not sure if brachytherapy procedures are performed transrectal. Oh, I see. That's a no. So I think there, with the transrectal approach, there are a lot of infections or risk on infections, so it's not happening right now.
The next presentation will be done by Professor Ashraf Labib from University of Portsmouth, UK. It will be done now.
So it's about the real-time calculation of the sterable needle for the optimized brachytherapy, and apologies for the delay. The role of the, as Professor Merzouki and Sarah has mentioned before, that this is an overall like flow chart of the different partners and what each of them is contributing. Our role really is to focus on the trajectory planning, which is this bit here at the top of the screen. This would have an input coming from the calculations, and the output goes to the software interface, to the robot guide, which will then go to the either to do the biopsy module or the LDR or HDR, what we're focusing on the LDR. LDR is the low dose radiation module. So it can do, as I said, both biopsy and LDR. So the main, this talk, I'm going to focus on the formulation and data structure used for the path planning and the real-time path adaptation program, as well as an automated algorithm for the needle trajectory planning in the context of robot brachytherapy and biopsy. So in terms of the two main criteria, we have to achieve an adequate dose distribution as closely as possible, but at the same time, we have to minimize the number of needle insertions. So we are optimizing the path of the needle of that route. In this work, it has been assumed that the seed plan has already been prepared and fed to the trajectory planning algorithm using the conventional seed planning methods. Also, it has been assumed that the orientation of the seeds can change with respect to the original plan without violating the radiation field requirements. I will go back to this latest assumption about the reorientation because it's really vital in our case because of the design of the needle itself. So the main challenges here is that we want to avoid the organs at risk, like the urethra and the bladder, the uncertainty due to the organ moving, and the radiation field from seeds is dependent on its alignment. So we developed like an integrated approach based on C++ that have the MRI feedback simulated into real-time module, and we have the robot controller that would lead to the robot inventor, which is simulated by the University of Lille. So the main innovation here, as well, one of the main innovations is that the needle, the algorithm is made for a needle design developed by University of Delft in the Netherlands, and they are going to present about the design in more detail later on, comprising of straight rigid cannula and a pre-bent stylus that keeps it intended curvature once deployed inside the patient's body. So the algorithm assumes a circular curvature for this stylus, and this circular curvature give us or give the robot more flexibility, so that we can reach areas or avoid areas which needs to be avoided. So we know from this operation that one of the most important part of the success of this operation is to avoid the neurovascular bundles. Otherwise, the patients might have side effects and so on. So the advantage of having this circular of curvature is to do exactly that. So the algorithm is required to minimize the patient trauma by minimizing the needle movements and the number of insertion using oblique insertions. And the seed usually is placed at the accuracy of 1 millimeter. Usually you would have because we are assuming that this is coming to the seed plan is coming, assuming that it is a straight needle. Usually you will have coordinates of two types of information, the X and Y, as well as the number of seeds for every needle that go through this grid, which Sarah has shared with you earlier on. The result of what we have developed is that we can actually do this sort of calculation in between 6 to 9 seconds to plan the trajectory. But the main limitation is that we are assuming here that it's straight needles because the plan is coming as a straight needle. But we then generate different scenarios, and instead of having straight needles going through the prostate, we would have one needle through the robot, which is curvature, but it generates the same, or it tried to reach the same amount of targets as the straight needles would do, the multiple straight needles would do. And this is really one of the main objectives of this project, is to minimize the insertions of number of needles as well. So we developed like a contour for the finite element analysis, and we also simulated the organs at risk, like the urethra, and the path of the needle itself. As you can see here, so how and to avoid and to measure the distance with the urethra. And one of the most important assumptions to be noted here, as I mentioned before, is that the plan is that the needles or the generation of the orientation of the seeds, if they change, they will not affect the radiation of the dose radiation calculation. So whether the seeds, just to let you know, is the size of it is like the size of a piece of rice. So if it is reoriented in a different direction, because it's not a straight needle, this will not affect the total radiation of the whole volume of the prostate. This is one of the, because this is one of the KPIs, or the key performance indicators of how much radiation did we cover through the insertion of the needle of the seeds by the needles. The system would generate the curvatures, the different curvatures, and based on the calculations, it will decide where to place the seeds. We had obviously to have some sort of weighting factors, because our algorithm assign weights to different criteria. This is a very classical multiple criteria decision-making method. So we are looking, for example, at a weight, and we got this weights from discussion with urologists from Queen Alexandra Hospital. So, for example, how much weight should we give to the tissue damage inside the prostate versus the tissue damage outside the prostate, for example, just to give you an idea about the weighting mechanism which goes into this algorithm. And then we also want to, so taking into consideration the minimization of the weight tissue damage, we generate the different scenarios, and we choose the scenario for the robot that, or for the needle path, that would achieve as many of this objective as possible. And you can see here, then it would say, okay, put this needle, and obviously it generates different forms, and the new algorithm, the act of penetrating the prostate causes movement and deformation, after which the correction mechanism is required. the stylet should be pushed out when the cannula is inside the prostate to maintain the collection mechanism, but we cannot pull the needle out. So this is again one of the constraints, because medically, once you pull the needle out of the patient, you have to change the needle. You cannot insert the same needle again. So to avoid that, we keep the needle inside the patient, but outside of the prostate if we can. So the traditional one has a straight needle, whereas in our case there is an angle to the insertion itself. And here is the trajectory algorithm that has been developed by our team. And you can see the prostate in blue color, in light blue color, and the organs at risk in yellowish color, and then the different scenarios that are generated by the model. And this is another view of the different scenarios that the system would generate. So this software has been designed in such a way to be user-friendly. So this is the user interface of the software, which shows the different parameters or the different weights, for example, that can be assigned to different aspects of the for the calculations. And just to show you the idea of suboptimality or the trade-offs that being done, for example, here we have both plans, seed plans, we are reaching the same acceptable radiation field. Whereas in seed plan A, we have an optimal trajectory. In plan B or second plan 2, we have suboptimal trajectory. Whereas the advantage of plan A is we have single insertion over multiple insertions in plan 2. So as you can see here, you are always trading off between different factors when you are doing such methodology. And this is really the problem which we are trying to address, is how do we give which weights, different weights to different criteria, and we try to find the optimum solution based on that. So the potential advantage of the Cobra project through this method is that the neurovascular bundles would be hopefully saved or not damaged. As we know from the current statistics, 50% of patients suffer from ED, erectile dysfunction. And also the other advantage is that usually this operation is limited to the size of the prostate. So if it's a large size, like more than 50 centimeters cube volume, it will not qualify to do brachytherapy in the first place. Whereas with our method that we have this curvature, which gives sort of flexibility, and we can reach different areas and so on, we can extend the number of patients who would be qualified to do this more accurate or more precise method, which is a treatment, which is the brachytherapy treatment. So as a conclusion, the fundamental limitation of this method, which is caused by the fact that the seed planning has been done separately from the trajectory planning. This is the main advantage, which we think in the future follow-up on this project, we should combine both the seed planning and the trajectory planning. And also, the problem here is that in conventional planning, we have stranded seeds, whereas in our method, the main limitation that we cannot use stranded seeds because of the curvature in the needle. So to avoid migration of the seeds outside the prostate. Nevertheless, in terms of biopsy, we satisfy all the requirements. So in terms of LDR, we are still lacking behind because of this lack of stranded planning seeds. But in terms of biopsy, we satisfy all the requirements. So it is envisioned that experiments will validate the proposed approach, as Professor Marzuki was mentioning, that this will be tested on dogs in the future. And that future research can be done to explore the use of machine learning, deep learning, to optimize the weights of these different criteria. Thank you very much.
The next presentation is registered presentation of Kevin from Cancer Center Oscar Lambret of Lille, which is not available today to present it.
Hi, I'm Kevin Bouboni, and I've been working on the real-time dose calculation on MRI during my PhD in the Oscar Lambret Center. The goal of the Cobra project is to build a brachytherapy device under MRI guidance. This implies numerous challenges, and at Oscar Lambret Center, we have been working on two aspects. On one hand, a solution robust to MR intensity variability, since every MR acquisition can be different according to the machine constructor, sequence, and acquisition parameters. On the second hand, the use of this device in real time. Those calculations cannot be performed directly on MR images since there is no correlation between MR intensities and electron densities needed to calculate the dose distribution in the medium. So the goal here is to convert an MRI into a CT. This image-to-image translation problem is often referred in the literature as synthetic CT generation. In terms of image generation, Generative Adversarial Network, GAN, works extremely well. Based on deep learning, the solution is fast and accurate. The learning of the GAN can be done with paired data. In paired fashion, the input MR and ground truth CT slices correspond to the same patient at the same anatomical localization. An elastic registration is used, which is time-consuming, but allowed to use a relatively simple model, so less data. In the second study, we investigated the synthetic CT generation with an unpaired dataset. Unpaired datasets have the advantage of being simple to create. They can be used with an unpaired data-friendly model directly in theory without any formal registration between the MR and CT. Even if in practice we choose to perform rigid registration in order to make the training easier. Models based on unpaired fashion use CT and MR slice on different patients at different anatomical localization during training. The baseline for that is to build first a dataset with sufficient patients for training and validation. CT and MR scans were not necessarily accurate on the same day. The median interval between the scans was 2 days. Interscan differences were therefore not taken into account in this study. We have for study 11 to 19 patients for training. This may not seem like much, but it's a 2-day generation, so multiplied by 90 slices, we are up to 1,700 pairs of CT MRI. This number is double with data augmentation, an operation which simulates new image based on flipping, rotation, and other geometric deformation. In our two studies, the validation has been performed using patients coming from 1 or 2 sites not included in the training to assess the generalization of our models. To begin with, in paired fashion, our architecture is based on the Pixopix HD, whose motivation is to improve photorealism of the outputs when inputs are high-resolution image. The traditional conditional GAN architecture is modified regarding two important aspects. First, we use two discriminators working at different scale, enhancing coarse to fine detail, very important for bone generation. Then a quadratic cross-entropy loss is used, which has the advantage to not just say if an image is fake or real, but how real or fake it is. Contrary to paired-based model, unpaired-based models are much more complex, needing therefore more data. It's a rule of thumb. I will not go deep in explanation, but the idea behind this architecture is since there is no ground truth to compare with the output, we generate first a synthetic CT with a first generator, then from the synthetic CT we generate a synthetic MRI with a second generator. The synthetic MRI is the output that we compare with the initial MRI for optimization purpose. Our architecture is based on the augmented cycle GAN. Visually speaking, CT synthesis took on average 7 seconds on the GPU for around 90 slices. As expected, differences are most pronounced in the bone structures, since they are not visible clearly on the MRI unless using an ultra-short sequence. Concerning the dose, when we apply the same treatment plan on the SCT, the SCTs tend to have higher Hounsfield units, resulting in a global decreased dose inside the body. Inner negative dose differences are often due to lower Hounsfield units on the synthetic CT in bone area or hair pocket not generated in the synthetic CT. Relative dose difference for higher dose are below 1%. This approach present is one of the very first allowing to derive a robust neural network trained and tested with data coming from different medical imaging centers. Without ever having seen an image from a test site, our models learn to synthesize a clinically acceptable synthetic CT, which may be generalized to different MRI manufacturers. This process has the capability to tackle the image variability problem in clinical practices, since change can happen in image acquisition parameter or with machine replacement, for instance. This study was done using standard morphological sequence without the need of any dedicated sequences. Then, even if we obtain the electron density, compute an accurate dose distribution in a matter of seconds is quite impossible. That's why, once again, we are looking for a deep learning solution to predict a Monte Carlo dose distribution. The problem is that the TG43 is currently used in clinical routine, but suffers from a lot of assumptions. Accurate dose calculation can be achieved with model-based dose calculation algorithm, with the Monte Carlo method being the gold standard. Monte Carlo methods use computer CT or MRI to assign voxel by voxel tissue mass density and elemental composition to calculate dose to medium. Similar information is always provided for the radiation source and applicator. However, traditional central processing unit-based Monte Carlo calculations are not optimal for clinical application in real time because of the slow computational speed. Accuracy of the absorbed dose calculated with the Monte Carlo method ties closely with the number of primary particles involved in the simulation. For the data preparation, we need to know exactly the input needed to perform the dose prediction. First, the MR, by converting it into a synthetic CT, gives the information related to the electron density. Second, a treatment plan in which we extract the 3D position of the sources into a 3D matrix called here soft treatment plan. Finally, we align these two volumes for ease of use. Even if deep learning for inference is fast, 3D is still a challenge. That's why we encode the synthetic CT using a feature-wise linear modulation generator. It allows to condition information by extracting in the synthetic CT only important feature need to translate the soft treatment plan in the dose distribution. We do not have sufficient Monte Carlo data for training, therefore we replace it with dose computing on a treatment planning system. This step is known as transfer learning. We do not perform quantitative evaluation, but proof of convergence has been made. Thank you for your attention. Bye.
Yes, now we go to the talk of Peter from DENCOM on the biopsy module. Thank you, Peter.
Yes. Good afternoon, everyone. My name is Pieter Wiskerke. I'm from Demcom, which is a mechatronic engineering company based in the Netherlands. And within this project, we had the task of developing and building a biopsy module, which would then be integrated in the robotic system that Polytech Lille has developed. And obviously the module has to be MRI safe, but also the restrictions on the dimensions that we could use were also quite challenging. Oops. Basically here you see the results of I see it there. Here you see the results of what we have developed. At least here you see the outside of it, and also the interface to the robotic system. But obviously it's more interesting what's on the inside of the module. Oh, all the way, sorry. Oh, too fast. Yeah. So basically, like I said, the dimensional restrictions were quite challenging. That's why we put a lot of effort to operate the biopsy needle with only one pneumatic cylinder. And that cylinder we actually developed together with Festo, which is a large pneumatics company in Germany. So they together we developed this pneumatic cylinder that is MRI safe. And this single cylinder is capable of operating all the actions that the needle needs to do. And besides this cylinder, we also added an ultrasonic motor. And that can be used to also rotate the needle, because also from literature we have understood that in some cases this rotation can help to guide the needle in the right direction. So here just a cross section of the inner side of the needle, and the mechanical mechanism that was developed to enable the single cylinder operation. And here you see then the result of the prototype that we built from it. And obviously we have tested the module in an MRI. It was a 1.5 Tesla MRI from the University of Twente, which we could use. Here you see just some example pictures of those tests with the Phantom. And basically from that, our conclusions were that there were no artifacts or distortions detected from the materials used. Also no distortion from the encoder signal in both the static and the active MRI fields. Also with the motor activation, we detected at least no issues. There was some added noise detected when the motor was actively moving, but what we have seen, it was very limited. After this work, we have transferred the biopsy module to the University, to the Polytech of Lille, where it is now integrated in the robotic system. And I was today very happy to see this system for the first time in reality. Obviously, I had seen pictures, but it's very nice to see this integrated work.
Yeah, thank you, Peter.
Thank you.
Thank you. Oops. So we will see a demonstration after on the biopsy module, and we are happy to use it 2 weeks ago with on live animal tests. We are happy with this collaboration with Demcom. Thank you so much, Peter. The next presentation, it's me. Well, okay. Okay. Yeah. Here briefly, I want to share with you how the process of the integration of the overall system has been done rapidly. You can see on this slide that the development and the integration of the Cobra project follow what we see the V diagram. It's well known here from designing and integration point of view. We started in 2018 with just requirement and specification coming from our clinical partners about what they want to need. Of course, we have here in our ecosystem at least two medical partners with two different practice, and the aim is to converge to a common tool or common device that can satisfy all the partners. So we took globally 1 year to define all the requirement and specifications. Then we started in 2019 the design in terms of simulation modeling. When I said design, here means the robot guide, the module of biopsy, and the module of brachytherapy that previously has been presented. Of course, we took a lot of time or a lot of actions to know which is the best placement or positioning of the patient here in the lithotomy position to identify the workspace that we can offer to the robot. We reached by 2019 the TRL3 after the simulation, and we started the first prototype version on 2020. After the first tests on MR with the simple human-machine interface, we started the integration of this version of the robot that will see it through the coming demonstration. In 2021, we reached this TL5 after testing on human and animal cadavers. And a few days ago, we did our first on live animal demonstration on dogs. This is our, let's say, our job of Cobra will finish at this stage, and we hope by the future of this project to facilitate or to accelerate the entry of the product or this solution in the real market. Good. This slide has been presented by our friend Ashraf. Just to see here, we have two levels of integration: hardware in the bottom side with different modules and bricks developed by each partners and the associated here, and the software part, which include offline development and online test or piloting. Here you have the clinical workflow. The clinical workflow means the process of the MR robotized brachytherapy, which is divided in 3 parts: pre-treatment phase, the online treatment phase, and post-treatment phase. The pre-treatment phase combines the preparation of the data, the dosimetry planning, and finally the robot planning in terms of dose, in terms of needle, what we see before, and robot. And online development or treatment phase, here the execution of the task and the safety of the process, where the post treatment phase concerns the dataization and the maintenance and the feedback of the test. The equivalent workflow for the biopsy or robotized biopsy, it's pretty similar globally, only to the brachytherapy. There is only the dose calculation is not considered here for the pre-treatment. The team worked initially first on the positioning of the technology of mini-invasive MR compatible robot, where we comparing with the different existing technologies in terms of MR devices, the quality of the images, etc. Yeah, there is a here you can see a review of this of these technologies and the positioning of Cobra comparing to them. The kinematics of the robot has been considered according or developed according to the available work space offered in all the MR with the based on the Unilift, which is a facility provided by one of our observers, which are NORAS. Allow us to identify the optimal placement of the robot according to the patient. Okay, then the control of the robot in real condition of MR has been done through piezoelectric motors. Here is a 5 degrees of freedom robot, and detailed work, the detailed development on this control, has been published in this version on this reference. Finally, the test on MR with this robot guide, which can support at the same time the biopsy module and the brachytherapy module, has been tested in real conditions to identify the ratio between the noises or signal and noises with the 3D Tesla MR. Finally, the interfacing with the emulated environment. This is what my colleague will present after. Has been first the test of the feasibility of the accuracy of the needle tracking has been tested on bio-inspired phantom. With the strong participation of our colleagues Stefan and Christian. This is what Mario in the coming presentation will give you in detail. Globally, this is the common one of our main output in Cobra is to develop a common platform or technological platform for all the project results. This is what we have here in the lab, actually, and the aim that we want at the end that this platform can be used for training through simulation facilities of the mini-invasive MR intervention. A rapid view about the last tests on the last demonstrations with on live animals did in the beginning of this month. Here we are using we used an MR scan of General Electric with 1.5 Tesla. Here you can see the dog reanimated, and here the view of the robot guide supporting the biopsy module developed by Dencom. Here the placement here in this last test we worked on the teleoperation mode, not full autonomous one. Why? Because it due to the anatomy of the animal, we didn't have it initially to to generate automatically the plan of the needle. So we worked in the mode of see and wait. That means we see the feedback from the images, and then we insert the needle progressively according to the online feedback from the image. Okay, here you can have you can see the human machine interface for use it for teleoperating this mini-invasive robot with the feedback here on MRC camera, which is an MR compatible camera of one of our partner observer. We can see also that the operator here is controlling or the control here is considering the operator in the loop. That means we need the feedback from the MR images, and we adjust the control here through this teleoperation console. We can see here, for example, for one insertion, the advantage of using the technology of Cobra. That means here we can make an oblique insertion. Here we have the location of the prostate for this dog, and the insertion here was made oblique. This to avoid organ of risk if we go longitudinally here. The distance between perineal skin here and the dog prostate is about 7 centimeter for this small animal comparing to human, which is 3 to 3.5 centimeter. Good, thank you so much for your listening. Okay, I give the talk to my colleagues Mario and Sarah to concerning the talk concern the bio-inspired prostate phantom design and test. Thank you.
Thank you, Professor. So, hello everyone. In this talk, I'm going to show you a little bit of the work that has been done on phantoms. So pretty much every partner in here has made their own phantoms for a specific application. And there is one particular that I'm going to develop. So I'm going to talk first about what is the Cobra bio-inspired phantom and the specifications, what we did with those specifications, and what has been done regarding in the engineering standpoint and also the clinical tests, because it's after all what's important for us, and some other work that Sarah will talk you about. So this is the concept of the bio-inspired phantom. This is the first version, and you have just a prostate made out of silicon, and what we want to do with it is testing and validating the robot. So one of the main problems is that we don't have enough database of patients in lithotomy position, and so we want to replace that partially with the data we have and the phantom. We wanted to move under these conditions of MRI. The prostate is way more mobile than with the regular ones, keeping in mind that the rectal ultrasound probe and usually they put pins to hold the prostate in place. They're not there anymore, so the prostate is way more mobile, and it can affect the outcome. Plus, we want to explore inflammation, which is something that nobody can see so far because there is no real-time imaging that is precise enough to assess this So what we developed is just kind of well, this is the first prototype. We improved the geometry afterwards, and you will see a demo of it working. It's just a ball with some cavities. Those are the colored arms that attach the prostate to the frame. And also there is an internal cavity, and those are air cavities that are attached to pressure sensors, and this information goes to a PC. Now I'm going to show you the video so you can see clearly how this works. And so this is a publication that was submitted for a journal, and you can see the whole concept in here. Yeah, in this video, we are seeing, but not online. So that's it. So in this video, we showcased pretty much the engineering standpoint of the Phantom. So we use it to validate the motion of the robot, the migration of the targets, and so it means that we need to assess the accuracy of the own Phantom itself. So in this publication, we performed some tests on it. Here you can see it coupled with the simulator, which can give in real time the position, the orientation, and also the indentation provoked by the needle during insertion, and also inflammation through inflation of this internal cavity. And you can see that actually you can interact with it in real time. That is what you are going to see live a little later, but with the new version of the Phantom, which is way prettier, actually. And it actually can be seen as some sort of input device or interaction device, or even a soft robot itself. It depends on the point of view, but for the medical interest, this is what we want to emulate: seed migration through either motion of the prostate itself or through, information, as you can see here. So obviously, this doesn't happen in the actual medical conditions, but nevertheless, the urethra is not is an organ at risk, so it's a part of the prostate we want to keep away from. So it seemed like a good target to place the cavity. And of course, those are just test from engineering standpoint, and we performed many others. Thank you. So well, just going quickly about that. This is how we manufacture the prostate. So it's something that can be personalized quite quickly and updated in the loop with even we've made a couple of tests with real patient-specific data. So it can be used for very specific shapes or positionings of prostate. And this is how the workflow software-wise goes. So the important part here is what is on the right of your screens, which is SOFA. SOFA is the simulator that recovers all this information. And SOFA is very powerful. It has been developed for medical simulation, and it's made for multiphysics interactions. So it can handle deformation and continuum mechanics. It can handle multiphysics actuation and even contact and nonlinear interactions. So this is where all the magic happens. And I'm going to let Sarah talk about the tests with the doctors. There you go.
So we worked with the Lille group to establish the specifications for the Phantoms in terms of the anatomical geometry and the movement and rotations, etc., of the prostate. And then we did some testing with the urologists at Portsmouth Hospital to give us an idea as to how near or possibly how far away we were from a kind of real life feel when inserting the needles. So for the study design, we actually had 5 different Phantoms. 2 of them were from the University of Lille, the bio-inspired Phantom that Mario has told us about. And they just had slightly different capsule thicknesses, and the capsule was made from silicon. We had a prostate Phantom prototype from another hospital that had no capsule at all. And we had two prototypes from our own hospital, again, with rubber capsules in different thicknesses. And so for the study design, all the phantoms were enclosed in identical containers just to make sure that they all looked exactly the same. A biopsy needle was used throughout. The urologist had access to the ultrasound so that they could visualize the movement and deformation of the prostate. And all the urologists answered the questions in the questionnaire independently. I won't go through the results in detail, but just to give you a couple of the highlights. The first lot of questions related to the interaction of the needle with the tissue. And what we found was that the Phantom C, which had no prostate capsule at all, was generally failing the tests for the interactions, and demonstrated to us that there is a need to have that capsule on the prostate to give that little bit of additional force when the prostate capsule itself is pierced. We found that the bio-inspired Phantom with the thick silicon wall was a bit too thick and it was giving a little bit too much resistance, and the thinner one was preferable. And we found that the Phantom from Portsmouth with the rubber spray around the outside, but whilst that worked quite well to give a good interaction with the force, it didn't grip the needle at all when the needle was being inserted through the prostate tissue, so it didn't give the right feel as the needle was traversing the prostate. We then had some questions relating to prostate movement and deformation. And in general, it was found that the movement was working pretty well with the bio-inspired Phantom from Lille Hospital. And we had some summary questions, which was just to ask the urologist which they felt was most closely relating to a real life prostate situation. And it was a little bit split, but the majority of the votes were for the bio-inspired Phantom with the thin silicon wall. And we had some qualifying questions as well, just to establish the experience of the urologist, how many cases they'd done with brachytherapy and biopsy, for example. Okay, so that was the testing with the urologists, and I'll hand back to Mario.
Yeah, so thank you. Okay. So as I said earlier, we performed some validation and mostly geometrical validation. So in here you can see what we measured with the simulation respecting the tracking that we used. And we also obviously put it on the MRI. This whole project goes on MRI, so this Phantom had to go in there. So what you're going to see is just a recording of the simulation with actual data that we got on real time on MRI. So these vibrations that you can see are actual vibrations of the table. The device is very sensitive and can measure those vibrations. And what you're going to see here is how it reacts to a needle insertion. And this is very brief. Sometimes we get problems recording this data, but this is how the Phantom acts on real time MRI acquisition. This, yes. This means that we can actually use it for tests, for training doctors, and even I'm not going to show you here that, but we have also MRI simulation, meaning that with static MRI take, we can train and we can get the live video, well, the static MRI deformated with respect to the prostate. Sorry, yeah.
Oh, fine, thank you. So just 2 slides to show you some of the additional Phantom work that's been done. Fairly early on in the project at Portsmouth, we developed a quality assurance Phantom, and the purpose of this was to give us some information on how accurately we can detect the true seed position and the true needle tip position. So we used a prostate tissue mimicking material for this with oil around the outside, and we had very specific fixed geometric arrangements with known positions and clinically relevant arrangements of seeds. So this is the sort of thing that would be useful when we use the Cobra Phantom clinically to establish what type of MRI protocols are giving us the best accuracy for detecting seeds and needle tips. And secondly, we also have developed an anthropomorphic phantom, and we did some tests on this in the real-time MRI at Lille. And the purpose of this phantom is that we have an option which is mobile. So inserting the needles will make the prostate move slightly in the way that it does clinically. And we also have a fixed geometry setup as well. So we can test the robot in those two different scenarios. And we've introduced a nice target material. So we have spherical lesions in there, which when you fire the biopsy needle, extracts the tissue clearly so that you can see how well you've hit the target, whether you were right through the center or whether you were slightly away from the edge. So it gives us some indication as to the accuracy of the robot with the biopsy gun. Thank you.
Thank you, Sarah. Thank you, Mario. Yes, we are. Now we go back for the feedback on animal tests from Thomas.
Good afternoon, everyone. So I'm Thomas Zarzeski from OCR, and I'm a clinical project leader. And I will follow Professor Merzuki's presentation about animal tests, and I will go in details with what has been done during these tests. So what was the aim? The aim was to achieve biopsies with the robot in living animals under functional MR environment. So these tests were organized in Lyon on the veterinary campus site. Why? Because this has been the multidisciplinary and collaborative effort between different teams. So the Cristal team that developed the robot, we as OCR, and also several partners from the Lyon campus site. So we had the help from BioVivo, which were the animal facility that could provide us the dogs. We also had the help of Oxel, which was the MRI facility and was specially dedicated to research programs on animals. And we had the support of one resident of the Veta Grossup Veterinary School, which is a surgeon. So the goal was to, as I said, to achieve biopsies. Some details about, sorry. So the test, as Roger said, was performed beginning of the month of June. So as I said, it was to perform biopsies. We did the test on 2 LC laboratory dogs, which are Beagle breed. They were 3 years old, and they were standardized around 11 kilograms. So the dogs were acclimatized for 10 days before the procedure. And 6 days before the procedure, we asked for our observer Nanovi to provide us some MRI markers to be injected in the prostate, first to have some targets, to have some targets, yes. And the day of the procedure, so the dog was anesthetized and the acquisition were made. The biopsy was supposed to be collected with the robot. So this was the ideal schedule that was planned. But these are the results for the 2 dogs. for the first dog, we first had the opportunity to correctly visualize the markers that were injected by the vet directly inside the prostate. So what was difficult was to, after first acquisition, we had to schedule and to determine the best trajectory to avoid critical organs, for example, glands, urethra, or the digestive tract, the rectum. So we had several trials to place the robot, to change the orientation. And we finally find the best angle and the best orientation of the robot to perform the biopsy and the insertion first. But due to the long time, we had to wake up the dog before the insertion. So what you can see here is the first observation that we made, that we correctly saw the markers in the prostate. So that was one good point that we achieved for the first dog. But for the second dog, it went better, since we had the opportunity to install the dog directly in the correct position, and the robot was also oriented in the correct position. As you may see, the MR images were of good quality, despite some issues, technical issues, for example, interferences with the MRI, and also some stiffness of the muscle with the long needle. So we had the opportunity to use the biopsy module to collect one tissue sample, and this sample is currently in the process in our lab to I do not have the results yet, but we are currently investigating if the tissue that was collected is indeed some prostate tissue. And you also have here the images that was presented by Rojdi previously. Is that on this slide we clearly see that the needle was in the correct place, and it was oriented as planned to target the biopsy, the prostate, sorry. So for both dogs, what is important to notice is that all animal welfare rules were followed closely. So there was no exceeding of the anesthesia time, and they was followed up closely after waking up. What is good also is that the dog recovered well. It was a mini invasive procedure, so they are now recovering and resting quietly. And as it was some minor procedure, they will be offered for adoption through an association. So that's one good point too. Regarding the limits of the test, we had to plan the trajectory once the dog was asleep. So that's what Rojdi told you before, is that it's the see and wait strategy. And it was difficult, time consuming. So that's why the first dog could not benefit from the biopsy. And despite injection of the markers, they have not been targeted, because first, the main objective was to focus on reaching the prostate. But we are confident on the fact that other tests can be performed soon. And also what is important to note is that in general, in veterinary practice, the perineal approach, just like the as the Cobra project is aiming, it's not commonly used due to difference in anatomy between men and dogs, and they would rather go for abdominal approach. So that's one limit that that came to us. But one good point is that these tests are very encouraging for the future, and it will also be interesting for clinical practice in dogs. For example, prostatic cancer in dogs can also be one medical issue that can be assessed with the with the robot, and we hope that in the future we can also work on other organs biopsy, and we think it's a very good point to go to human after that. So thank you very much for your attention. It was quick, but I hope that it will be okay for you.
Thank you, Thomas. Thank you, Thomas, for this feedback.